Welcome back to Deep Learning, and today we want to continue talking about convolutional neural networks, and the thing that we will learn about today is one of the most important building blocks of deep networks.
Instead of what humans might need just dozens of examples, these things will need millions, right? For very, very, very simple tasks.
So far we had those fully connected layers where each input is connected to each node. This is very powerful because it can represent any kind of linear relationship between the inputs. Essentially, between every layer, we have one matrix multiplication.
Of course, we are building on all these great abstractions that people have invented over the millennia, such as matrix multiplications.
This essentially means that from one layer to another layer, we can have an entire change of representation. And this also means that we have a lot of connections. Let's think about images, videos, sounds in machine learning. Then this is a bit of a disadvantage because they typically have huge input sizes. And you want to think about how to deal with these large input sizes.
Image recognition or something like that?
Let's say we assume we have an image with 512 times 512 pixels. That means that one hidden layer with 8 neurons has already 512 to the power of 2 plus 1 for the bias times 8 trainable weights. And this means that's more than 2 million trainable weights just for a single hidden layer. Of course, this is not the way to go, and size is really a problem. And there's more to that. So let's say we want to classify between a cat and a dog. If you look at those two images, then you can see that a large part of these images, they just contain empty areas. So they are not very relevant. So pixels in general are very bad features. They're highly correlated, they're scale dependent, they have intensity variations, so they're a huge problem. So pixels in general are a bad representation from a machine learning point of view. You want to create something that is more abstract and is summarizing the information better. So the question is, can we find a better representation? And we have a certain degree of locality, of course, in an image. So we can try to find the same macro features at different locations and then reuse them. Ideally, we want to construct something like a hierarchy of features, where we have edges and corners that then form eyes, then we have eyes, nose, and ears that form a face, and then face, body, and legs will finally form an animal. So composition matters, and if you can learn a better representation, then you can also classify better. So this is really key, and what we often see in the convolutional neural networks, on the early layers you find very simple descriptors, and then in the intermediate layers you find more abstract representations here, like eyes and noses and so on, and then in the higher layers you find really receptors, for example here, faces. So we want to have a local sensitivity, but then we want to scale them over the entire network in order to also model these layers of abstraction. And yeah, we can do that by using convolutional neural networks. So here is generally the idea of such architectures. You, instead of fully connecting everything with everything, they use a so-called receptive field for every neuron that is like a filter kernel, and then they compute the same weights over the entire image, essentially a convolution, and produce different of these feature maps. Then the feature maps go to a pooling layer. The pooling then tries to bring in the abstraction and to demagnify the image, where we then can go into the next stage where we produce convolution again, more layers and more feature maps. The feature maps are then summarized again by a pooling layer, and you go so on until you have some abstract representation, and the abstract representation is then fed to a fully connected layer, and this fully connected layer in the end maps to the final classes, which is like car, truck, van, and whatnot, and this is then the classification result.
deep learning is any kind of machine learning that involves learning parameters of more than one consecutive step.
So we need convolutional layers, we need activation functions, we need pooling to get the abstraction and to reduce the dimensionality, and then in the last layer, the fully connected one for classification. So let's start with the convolutional layers. So the idea here is that we want to exploit the spatial structure by only connecting pixels in a neighborhood. If we want to express this in a fully connected layer, we could set every entry in our matrix to 0, except they are connected by local connections. So this would mean that we can neglect many connections over spatial distances. And then another trick is that you use filters of size 3 by 3, 5 by 5, 7 by 7, and you want them to be identical over the entire layer. So the weights within the small neighborhood, they are the same even when you shift them around. So this is then called tied or shared weights. And if you do this, then you are essentially modeling a convolution. If you have the same weights, then this is exactly the same concept that you learn in any image processing class as filter masks. So we essentially here construct networks that have trainable filter masks. If you have attended a signal processing class, then you know that convolution can be expressed as the integral over two functions, where you shift one of the functions over the other and integrate over the entire domain to obtain the final result of the convolution. Cross-correlation is an associated concept, and you see that the only difference between cross-correlation and convolution is the sign for tau here. So in convolution, you move to the negative direction. In cross-correlation, you move to the positive direction. What we see quite often is that people talk about convolutions, but they actually implemented cross-correlation. So they're essentially flipped if you flip the kernel and vice versa. So if you are creating something that is trainable, it actually doesn't matter because you would learn the sign of the function anyway. So both implementations will be fine. And cross-correlation is actually frequently being implemented in actual deep learning software, and typically you initialize the weights randomly anyway. If you want to compute the convolution kernel at the very boundary pixels, your receptive field would actually reach outside of the field of view. So one way of dealing this is to reduce the size of the feature map in the next respective layer. Or what you can do is you can use padding. And what many people do is just zero padding. So all values that have not been observed are actually set to 0, and then you can remain in the same size and just convolve the entire image. There's also other strategies like mirroring and so on, but padding is probably the most common one. So then you get some forward pass, so you actually don't have to implement it with the small convolution kernels. You can also use a Fourier transform actually to perform the convolution. So you have the input image. Let's say it's a multi-channel image where, for example, S is the number of colors. And then you have this image. So you apply a 3D filter. And here you can see that in the spatial domain, you have the convolution kernel, but in S direction, it's fully connected across the channels. And if you do so, you can apply this kernel, and then you get exactly one output mask, because this is the kernel that you have convolved your image with, and then we return here this single output field. Now, if you had another feature map that has also a fully connected connection across the channels, then you can produce a second mask with the same padding, and this way you can then start constructing one feature map after another. Let's talk a bit about the convolution. Convolution is expressed as matrix multiplication with this matrix W, and there we're using a Toeplitz matrix. So this Toeplitz matrix is a circulant matrix. This is constructed by the weight sharing, meaning that if you're constructing this matrix, you have essentially the same number of weights in every row that is being trained, but they are shifted by 1, just because they are computing a different local field in every row, which means the same weights are just shifted. So this gives us a circulant matrix, but it means that we stay in the domain of
matrix multiplications.
So also our convolution can be implemented as matrix multiplication, and therefore we simply inherit the same formulas as for the fully connected layer. So if we want to backpropagate the error, it's simply the input error from the backpropagation times the weights transposed that is computed. And if you want to compute the update for the weights, it's essentially the error term multiplied with what we got from the input in the forward pass transposed. So it's exactly the same update formulas as we have seen them previously. Okay, so this is nice. There's not so much to keep in mind. Of course, you have to make sure that you get this weight sharing implemented correctly, which we'll show you in the exercises. But for us now, we can just treat it as
matrix multiplications.
One interesting thing that you see in the exercises is, by the way, that the backward pass can also be expressed as convolution, and you will see that in the exercises. Now, what have we gained with the convolutional layers? Well, if you now stack multiple filters, we get essentially a trainable filter bank. Let's say we have 8 filters, which means 8 nodes in a 5 by 5 neighborhood. Then we suddenly have 5 to the power of 2 times 8, 200 weights. And 200 weights is considerably smaller than the 2 million weights that we've seen before. So, nice thing again about convolution is it can be applied independent of the image size. So what we can do is we can convolve any kind of image with those filters, and then it just means that the activation maps that we are producing also change when we have a different input size. We will see that in one of the next lectures how this behaves, but the very nice thing here is that we have much more data to train for a single weight. There's also things like the strided convolutions. This is when you try to incorporate the pooling mechanism, the dimensionality reduction mechanism into the convolution, and this is things like skipping 1 pixel at each other. So with the stride S, we describe an offset, and then we intrinsically produce a activation map that has a lower dimension, and it actually has a lower dimension that is dependent on this stride. So this reduces the size of the output by a factor of S because we're skipping so many steps. And mathematically, this is simply convolution and subsampling at the same time. And we have this small animation here in order to show you how this is being implemented with stride 2. There's also things like dilated Artrous convolutions, and here the idea is that we are not increasing the stride, but we are increasing the spacing in between, and now the receptive field is no longer connected, but we are looking at individual pixels spread over this neighborhood, and this then gives us a wider receptive field with less parameters or weights. Another very interesting concept is the 1-by-1 convolution. So far we had H filters with these neighborhoods, and in depth we had S, but remember they were fully connected in the depth direction. And this is also really interesting because now if you have a 1-by-1 convolution, then this is essentially the same as a fully connected layer. So you simply have a fully connected layer over this single dimension, and you can then put an arbitrary input, and all what it does is it computes a reduced number of feature maps in the direction of the channels, because there we have the full connection. So essentially we can now do a channel compression with 1-by-1 convolutions. If you flatten the input to 1, by the way, and map everything into the channel direction, then 1-by-1 convolutions are fully connected layers. So we can essentially express also the entire concept of fully connected layers with 1-by-1 convolutions if we arrange the outputs in an appropriate way. So this was first described in the network paper that we will also talk about when we talk about architectures. And then these one-by-one convolutions simply calculate the inner products at each position. And this is a very nice method to decrease the size of a network, in particular to compress the channels. And it intrinsically learns the dimensionality reduction and can help you to reduce redundancy in your feature space.
Of the world in vector space. But I think this is very difficult for normal people to understand. They would not know what the heck they're looking at.
Equivalent but more flexible are, of course, n by n convolutions. Okay, next time in deep learning, we will talk about the pooling mechanism and how to reduce the size of the feature maps. No, not just using convolutions, strided or truth convolutions, but you can also model this explicitly in a pooling step, which we'll talk about in the next lecture. So thank you very much for listening and see you in the next lecture. Bye-bye.